Hey guys, this is day 3 on basic differentiation rules. Finally, we come to the day where we learn the shortcuts and the formulas that make your life 20 times easier. Except that's true and false at the same time. Yes, it'll be easier to calculate the derivatives, but now I'm going to throw a lot more of the complicated formula or the complicated equations at you, which you need to figure out the derivative of. So it's like a blessing and a curse in disguise, both at the same time, same but different. So let's go ahead and take a quick look at this. So this requires you to kind of go back to what we have from days 1 and 2 of this particular unit. Remember, we're in unit 9, not in unit 8 more, now that we're talking about derivatives and what they actually look like. So go back a couple of days here. I believe day 1 is when you guys actually talked about all this stuff, like up here. So we took the derivative of x squared, x cubed, we took the derivative of 1 over x, and then the square root of x. I think the only one we didn't do was x cubed. I'll give that one to you guys. Why not? So this one, when we take derivative way back when, we got this. So I'll give you that one at the very least. Okay. And so now you're like, okay, how did Mr. Wright know that so quickly? And there's some special rules that we can use, kind of like properties of exponents. Think about properties of logarithms, right? When you guys first learned logs, you guys are like, oh, this is annoying. Or things like sine and cosine, right? There's a lot of different properties you can utilize here. In the same way, derivatives, there's a lot of properties and shortcuts we can use because mathematicians have kind of figured out the patterns and made it more cohesive. So the first one's the easiest one right here. The first easy rule is if you take the derivative of any constant, meaning there's no variable in front of it, as in this case, there's no x in front of it, it's simply 0. So derivative of anything, 2, 5,000, pi, -3, they're all going to equal 0. So I'm going to skip number 1, that's easy. Number 2 is more of a sort of a nicety to have. If you have something like here, f of x equals 6x, so we're looking at this first one here, all you really end up needing to do is you just take the number in front of it. Or, better way to think about it is you're taking, what ends up happening is you take, effectively when you take derivative, you're doing 6 times the derivative of the x on the inside. So that's going to come in handy a little bit later. So same thing like over here, you can just kind of split it as 2. And then since that coefficient kind of goes in front, helps you out only focusing on what you need to focus on. Now, of course, we haven't talked about what is the derivative of, say, x or x squared or something with a variable that we're trying to solve for. Recall, again, just real quick, and not super important now, but when we get to higher order derivatives or like taking derivatives of different variables, keep in mind this crazy format here. It looks weird now, but it will make sense as time goes on, or make more sense. It's dy over dx. You're taking derivative of the y, or the function itself, in terms of the x value. So the x variable stuff is very important when you're doing all this. We'll get to it later on. Don't worry too much. I just want to make that clear up front. Let's take a look here. Yes. So going to the second part, we can also split it just like we do with most things. The additive property, if you're taking derivative of the entire thing and there's a sum, you can split the derivative up and take derivative of each of those components separately. You can do this with 3 terms, 4 terms, 5 terms, so on and so forth. And last but not least is the derivative of powers. This is extremely important. It's one of the most simplest, but also the most like intuitive of all of them. So once you get this one down, you'll be like, oh, this makes it so much easier. So basically, it kind of looks like series and sequences with this idea of like n and n minus 1, right? What you may want to think about is if we do, for example, let's do A. Actually, no, let's do B. Part of B. I'm going to do part of B. What you do is, okay, take derivative of the first part here. We have 4 terms. I'm going to take derivative of them separately, okay? So if you take the first term, notice it's a coefficient in front, so I can kind of like factor that 3 out or like kind of push it to the side. Don't really need to worry about it. So if you keep the 3 outside, let's now take derivative of x to the 4th. You bring the power down. So it's 4x. And then you raise the power, or you take that exponent and reduce it by 1. So now it becomes 4x cubed. Notice how we didn't do limits. Notice we didn't do anything with graphs. Notice we didn't do this crazy like one whole page of work. Shortcuts. So finally, multiply that 3 back in, and now you get this. You'll get quicker with this as time goes on. Some of you might think, oh, just multiply the 4 to the 3 and bring the 4 down to a 3, or subtract 1 from it, and boom, there you go, 12x cubed. That's the idea. When you get to things like radicals, you might think, wait, how we've never done with that. But turn the radical into an exponent. This is x to the 1/3. Same principle applies. Bring the exponent down, subtract 1 from the exponent. Yes, you will get negative exponents. That's totally fine, totally normal. And then go from there. Same thing with d. It's 1 over x cubed. Or 1 over x squared. We never talked about, quotient or anything like that. There's a quotient rule. We'll get there later. But this one, again, rearrange the entire fraction so that it's going to be x to the negative something power. Maybe a little hint there, okay? And you go on from there. These are funny ones here. This is kind of reminiscent of what you guys did with imaginary numbers. So if I go back to the beginning of algebra 2, or more like the middle of algebra 2, I should say. Remember, I squared is -1. I squared is going to be -1. I cubed is negative I to the 4th is equal to 1. And when you go to I to the 5th, it's actually repeating the cycle. It's in cycles of 4. Every time you have 4 of those, like, I guess, numbers in the sequence, it repeats the pattern over and over. There might be not the same pattern, but like there might be a similar pattern when you do it with sine. The reason why I say that is when you look at this one here, it says derivative of sine is cosine. Okay, that's something you just kind of need to kind of keep in mind and memorize. Take the derivative of cosine, you get negative sine. So what's the derivative of negative sine? So what I want you to do is kind of go over here. If you take the derivative of sine, right, over dx, you get cosine, right? And I'm going to have you try this. And should you have any questions, go ahead and ask me during office hours or just send me an email. You get negative sine x, right? Then continue the pattern. If you take the derivative of negative sine x, remember, what is that -1 in front of the sine? What does that basically allow us to do? Could we maybe factor it out or something of that sort? Maybe take it out because it doesn't get affected by derivative. See what happens then, and keep this process going. See how many times you do this, and maybe you'll see a pattern that develops. Knowing this now is going to be super helpful as time goes on. It's a niche kind of thing to know, but it is nice to have in like your back pocket, so that it's kind of like multiplication division. Like there's some fun things that you might recall or remember, like the 11s, 11 times 1, 11 times 2, 11 times 3, just like a shortcut. It just helps a little bit with the computation or the arithmetic as you get that from there. E to the x is very easy. It's just e to the x. This is probably one of the easiest ones until you start messing with the exponent. Okay, sorry about my light bulb. I don't know why it's flickering like that, so sorry if I get some black and white issues in there, so sorry about that. Once we get to the point where we start putting more things into that upper exponent part, it's going to get a little hectic. We're going to wait for that a little bit later once you go through all the basic rules, okay? So just worry about for now that if you see e to the x, it is a godsend. It's one of the easiest things to do. Natural log of x is going to be, or the derivative of that's going to be 1 over x, just some things you got to keep in mind there as well. And just recall again, we keep throwing at you what the definition of the derivative is, slope of the tangent line, Because when we get to this part here, we now ask for the example, what is the slope of the tangent line given at a particular x value, right? So I'm just going to pick one that might be a bit confusing here. Let's go ahead and, which one should we pick? They're all kind of the same. Let's do the equation one. This will combine all things together. Yeah, let's do this one. Let's do 8. 8's got an interesting one here with the square root. Okay. So what we're trying to do is first in the end game, we're trying to find the equation, okay? Well, in the equation, I need to know my y-intercept. I need to know my slope. So let's think here. Wait, slope, why is that important? Wait, slope of the tangent line at t equals 16. Find the derivative. So g prime of t is equal to, let's take the derivative. So t square root, okay, we don't have any specific formula for that, so let's rewrite it as an exponent. It's to the 1/2 plus 1. Or really, I should just start with that, g of t. And then take the derivative, now that we know what we're doing, pull the 1/2 down, subtract 1 from the exponent, we get -1/2. We'll clean this up in a second. And plus 1, derivative of 1 is just 0, it's a constant. So let's change this up from here. We get, if I basically clean this up, it's going to be 1 over 2 square root of t. Okay, I just did a couple things and a few steps there. That's basically what we did. Okay. So from there, we have basically found the slope, or the formula to find the slope. Now what we need to do is plug in, let's keep this going, g of t, plug in t equals 16. So we get 1 over 2 times 4, because square root of 16 is 4, so you get 1 over 8. We have now found the slope at t equals 16. We know this function, for your perspective, let me just make sure I get this right, yeah. Your perspective, square root of t is kind of like this function, it's a square root function. So in t 16, so like kind of way over here, we know that the slope of that tangent line is 1/8. Okay, good. So now that we got that, we just need to know a couple of things here. Maybe we should probably have started off with, I just realized this, probably should have just started off with what is g of 16. That might have been important. Have a t value, there should be a g value corresponding to it, or like if there's an x value, there's a y value corresponding to it. So that means it's going to be square root of 16 plus 1, which is simply 5. So now we have the coordinate, let me just write in red up here, we have the coordinate 16, 5. We have the slope, because the derivative is a slope. Okay, slope, 2 points, like x1, y1. Oh wait, slope intercept, or not slope intercept, sorry, point slope form. So let's bring this over here. We get y minus y1, which is 5, equals the slope 1/8, quantity x minus x1, which is 16, and now we simplify things out. So finally we get 1/8 x, that's going to be minus 2 plus 5, so it's plus 3. And there you go. That's your equation. That should be it for this part right here. Awesome. So again, individually, not bad, right? We had the derivative of powers rule there. We had to invert a couple things. That's fine. We had the derivative of constants right there. Not too bad. But it's when you put them all together that things get a little hectic. So if some of you think this is like really easy at first, just hold your horses. We got a couple of other things that we haven't really talked about yet. You'll see combinations of things. So we'll see like e to the x, and then we'll have the derivative of powers rule. E to the x is easy for now. We're not going to do anything crazy, no special cases just yet. And then up here, we got the sine function, right? You might have a combination of all these things together. So you just get fluent with understanding the rules and how they kind of apply with one another. Aside from that, and that you're probably yelling at me at why we didn't tell you this earlier. Again, said this multiple times over multiple videos. You're probably sick and tired of hearing me say it over and over, and I am as well. Other than that, you should be squared away. Hardest part is just rearranging the original function to make it work with the rules that you have. But that's usually how we work with mathematics in the first place. We've got to manipulate things and work things out in our favor. If there's something to at least help you with this one right here with the derivative of powers, start with something that's really high powered, so like x to the 7th power, right? Then take derivative of that. Okay, 7x to the 6th. Take the derivative of that. 42x to the 5th. And just keep practicing with this rule because this is the most important like fundamental that you have aside from the constant one. Constant's like super easy. If you see like 4 or 3, derivative of that is just 0. Piece of cake. But getting used to this is going to be helpful for you as you move on. So again, get the basics down, go from there.